In this video, we'll look at logarithmic functions and their relation to exponential functions. We'll learn how to convert back and forth between exponentials and logs, and how to solve log equations. Precalculus Online begins now. Section 5.4 Logarithmic Functions. So we're going to take a look at log functions today. And the first item up on this lesson is an exploration. So go ahead and follow the directions for the exploration. Complete this. It's a page and a half, so be sure and turn the page to the next page to complete the rest of it. And pause the video at this time, and then after you finish the exploration, come back and check your work. All right, so hopefully you had a chance to do the exploration, and let's go ahead and take a look at this. So we have f of x is equal to 2 to the x, and the graph of that is shown. That's the exponential that we studied in the previous section. It says go ahead and create a table of values for f of x. So, and we did this last time, so I'll just go ahead and fill this in quickly. And then it says create a table of values for f inverse. Well, we learned earlier in this chapter that in order to create the inverse function, all you do is you switch the x, y coordinates of a point on the original function. So let me write this out explicitly for this first one, and then we'll see the pattern here. So if we know that -3, 1/8 is on f, then the point that is on the inverse function is 1/8, -3. So all of these y values that are in this first column here, they go in the x's for the inverse. And all of the x's then become the new y values in the inverse function. Then it says, on the next page, it says plot the points for f inverse. I'm just going to take all of these points and plot them. So we have, let me start with 1, 0. Then we have 2, 1, 4, 2, and 8, 3. And then the fractional ones, these are a little bit more difficult, but no problem. 1/2, -1, 1/4, -2, and 1/8, -3. Then it says graph f inverse by connecting the points. So I'm going to connect them. Like so. There we go. Pretty good, not too bad. And it says remember that the graph of f inverse is the reflection of the graph of y equals f of x over what line? And that line is the line y equals x. And there you go. So notice a couple of other things here. Number 4, it says, what is the horizontal asymptote for f of x is equal to 2x? Well, the horizontal asymptote was y equals 0. And then number 5, what does the horizontal asymptote correspond to in the graph of y equals f inverse? So since we're trading x's for y's when we go from f to f inverse, we need to trade the y equals 0 for x equals 0, and that creates a vertical asymptote right here. So we have a vertical asymptote at x equals 0. And let's go ahead and complete the other questions here. So this was y equals x, y equals 0. It becomes a vertical asymptote at x equals 0. and then complete the following. What was the domain of f? Well, f was the exponential function, so it has the full domain from negative infinity to infinity, and the range was 0 to infinity. Then the question is, what is the domain of f inverse and the range of f inverse? When you find the inverse function, you switch the domain and range from the original function around. So the domain is going to be 0 to infinity, open at 0, and the range is negative infinity to infinity. So basically all we've done is we've taken the exponential function and we've found its inverse. And the good part about that is that actually has a name, and we give it here. If f of x is equal to a to the x for a greater than 0 and not equal to 1, then f inverse of x is known as the log in base a of x. In words, the logarithm function is the inverse of the exponential function. That's the relationship between logs and exponents. The log function is the inverse of the exponential function, and the exponential function is the inverse of the log function. Thus, we get this equivalence. So if I take a to the x power and that is equal to y, then there's a similar statement that I can create with logs, and that would be log base a of y is equal to x. So notice what the x is as the result of a log. It's the exponent in the original function, in the original equation. So oftentimes you'll hear me say that the log is merely the exponent that is needed to do something. In this case, x is the exponent that's needed to take a, you raise it to that power to get y. So a to the x is equal to y, and how do we find that exponent? Well, it's just the logarithm. Let's do some examples. Example 1, write 3 to the 5th is equal to 243 as a logarithm. So that would be log in base 3 of 243 is equal to 5. Notice that 5, again, is the exponent. Example 2, write log base 4 of c equals d as an exponential. So we take the base, 4, we raise it to the exponent. The exponent is what the log is equal to. The log is equal to d, so d is the exponent. And then the c, this part right here, is called the argument of the log. And the argument of the log is c, and that's what the result is when you do 4 to the d power. All right, example 3. Find the exact value of each without a calculator. So the first one, log base 2 of 8. So this is asking for the exponent 2 raised to what power is equal to 8. And you may know this one, and the answer is 3. So log base 2 of 8 is equal to 3. Next, let's look at B. Log base 9 of 9 is equal to what? So again, we can say 9 raised to what power is equal to 9? Well, 9 to the first power is 9, and so the answer is 1. Part C, log base 16 of 4. Now this one is not as easy, so I'm going to go ahead and call this one x. And we're going to set up an equation so that we can solve this one. If I turn this back into the exponential, I get 16 raised to the x power is equal to 4. And then we solve this equation just like we did in the previous section. We find the common base family and then change those into those bases via exponents. So 4 and 16 are both in the 4 family. 16 is 4 squared. The base family of 2 would have worked as well. but 4 is going to work for us. So we get 4 squared to the x power equals 4 to the first. Multiply the exponents. We get 4 to the 2x power is equal to 4 to the first. Set the exponents equal to each other. So 2x is equal to 1, and x is equal to 1/2. So instead of saying x, we actually say 1/2. Notice that an exponent of 1/2 is actually equivalent to a square root, because a square root is the half power. So, and that makes sense here. We're taking 16, a base of 16, and what do we need to do to 16 in order to get a 4? We need its square root. And so that means log base 16 of 4 is 1/2. Let's try D, log base 3 of 1/9. Again, I don't know this one. I'm going to call it x. And we'll set up an equation. So 3 to the x is equal to 1/9. We need to make the bases the same. So we'll have 3 to the x is equal to 3 to the negative 2 power. Where does the negative 2 power come from? Well, first off, I notice that I have a 9. In order to get a 9 using a power of 3, I need to square it. So there's the 2. But 3 squared is 9, not 1/9. If I want 1/9, I need the reciprocal. And in order to get a reciprocal, I use a negative exponent. So, and now this one is basically solved. So we get x is equal to negative 2. Let's take a look at the graphing of logarithms. So we're going to compare the properties of exponentials on the left side with the properties of logarithms on the right side. And the key here is that these two functions are inverses of each other, so their properties are related. So let's recap the properties of exponential functions. The domain is negative infinity to infinity. The range is 0 to infinity. X-intercepts, none. Y-intercept of 1. Horizontal asymptote, y equals 0. If a is greater than 1, then the exponential function is increasing. If a is between 0 and 1, then the exponential function is decreasing. The graph contains the points negative 1, comma 1 over a, 0, comma 1, and 1, comma a. And the graph of f is smooth and continuous. Now let's look at the properties of logs. What is the domain and the range of the log function? Well, the range and domain switch over from a function to its inverse. So the range of the exponential becomes the domain, and the domain of the exponential becomes the range. So the domain of the log function is 0 to infinity, and the range is negative infinity to infinity. Now what this means is that you can never take the log of 0 or any negative number. If you ever try to take the log of 0 or a negative number, you get undefined. If you do it in the calculator, you get an error. The number 2, the x and the y intercepts. Again, these switch around because the inverse switches x's and y's. So the x-intercept, there's only one, and it's a 1, but the y-intercept, there isn't none. There are none, because, again, you can't use x equals 0. The horizontal asymptote becomes a vertical asymptote at x equals 0. The increasing and decreasing part stays the same. So if the base of the log is greater than 1, it's increasing. If the base is between 0 and 1, then the log is a decreasing function. The points, they switch around exactly as you would imagine, and we get 1 over a comma negative 1, 1 comma 0, and a comma 1. And the graph of f, in this case the log function, is smooth and continuous. Let's look at example 4. Sketch the graph of y equals log base 5 of x. Identify the domain, the range, and the vertical asymptote. So here we go. We know that we have these 3 points on it. We have 1 comma 0. We have a comma 1. Well, the a in this case is 5. So 2, 3, 4, 5, comma 1. And then 1/5 comma negative 1 right here. We do have a vertical asymptote right there. And so here's the graph of the log base 5 of x. Looks like that. The domain is the set from the interval from 0 to infinity, open at 0. The range is negative infinity to infinity. We have a vertical asymptote of x equals 0. Now, let's talk a little bit about the shape of the log graph. Notice that in this section right here, as we continue to go out to the right, it looks like it's going to flatten out. In fact, it continues to increase forever. It's just very shallow. It does not rise steeply at all. And the further out you go, the flatter it gets. But it's still rising. And there is no upper bound to this. There is no some maximum horizontal asymptote number that it's going to approach as a flat line. It continues to rise forever. Example number 5. Sketch the graph of y equals log base 7 of x minus 4. Identify the domain, the range, and the vertical asymptote. So here we have transformation. And that transformation is 4 to the right, because we are taking the log of x minus 4. So the minus 4 is on the inside. That makes it a horizontal shift. And x minus 4 is 4 to the right. So let's graph the parent function of y equals log base 7 of x. And maybe that's too much. Okay. 1, 2, 3, 4, 5, 6, 7. So it's going to go through 1, 0, 7, 1, and then 1/7 negative 1. Like that. Let's mark these points. So 7, 1, 1, 0, and 1/7 negative 1. And then let's do the transformation. It's going to be 4 to the right. So 1, comma 0 is going to be moved over to 2, 3, 4, 5, comma 0. 7, comma 1 is going to be moved over to 11, comma 1. So 5, 6, 7, 8, 9, 10, 11, comma 1. Let's go ahead and do the asymptote next. The asymptote was at x equals 0. When we shift that over 4 units, it shifts over to x equals 4. This gives me a good guideline as to where the graph needs to go. So 1/7 plus 4 is 29 over 7. The shortcut for doing that is to do 7 times 4 plus 1. And that gives you the 29. Now let's find the domain. The domain is 4 to infinity because we shifted everything over 4 units to the right. The range is still negative infinity to infinity, and the vertical asymptote is x equals 4. Let's look at example 6. Sketch the graph of y equals 1 plus log base 1/2 of x. Identify the domain, the range, and the vertical asymptote. So a couple of things to notice first. We have a base of 1/2. So that's the base. And since that's between 0 and 1, it means we have the decreasing log function. So we'll have to handle that. And then we have 1 plus, so that is a vertical shift of 1 up. So first, let's draw the parent function. That is y equals log base 1/2 of x. Well, we still have 1, 0. We still have a, 1 as a number that we need to graph. But the a in this case is 1/2. So that's right here. I'm going to put that right there. So that's 1/2, a. Comma 1. And then the other point that we needed to graph was 1 over a, negative 1. But again, the a is 1/2. So 1 over 1/2, negative 1 would be 2, negative 1. So it comes out here. And there's 2, negative 1. We still have the vertical asymptote at y equals 0. And now let's draw this parent function graph. Similar to the increasing graph, where it goes on forever in that behavior, this one goes on forever in that behavior as well. It decreases forever. There is no lower bound number that it cannot exceed. It will find every number down there because the range is the full real number line. All right, but that's the parent function. Let's graph the shifted one. And the shift is 1 up. So this shouldn't be too bad. So instead of having 1, 0, we have 1, 1. Instead of 1/2, 1, we have 1/2, 2. And instead of 2, negative 1, we have 2, 0. It'll look something like this. We still have the vertical asymptote right there. And now we need to identify the domain, the range. So the domain is 0 to infinity. The range is negative infinity to infinity. And the vertical asymptote is still x equals 0. So the vertical shift did not affect any of the domain elements here, which is sort of the one to worry about for logs. All right, let's take a look at the special logarithms. We have a couple of special logarithms. In base 10, if you have a log in base 10, this is known as the common logarithm. And the notation is log of x. Notice that you do not use the 10 down here. The 10 is understood when it's missing from the logarithm. And this means, so y equals log of x means that 10 to the y power is equal to x. And you use the common log a lot when you're dealing with scientific notation and you're dealing with applications that are based on magnitude, like seismic readings and things of that nature. All right, there's another one. How about base e? This is known as the natural log. And the notation for that is ln of x. And this just means that if y is equal to ln of x, then e to the y power is equal to x. So natural log uses ln. You do not write the base e because since you're using a different symbol for log, you're not even spelling out log, you're using ln, then it's always going to be base e. For common log, you can write the 10, it's just uncommon to do so, and you should become fluent in reading it. If it says log, then at this point they're talking about base 10. Example 7. Let f of x equal natural log of x plus 2. Identify the domain, the range, and any asymptotes of f. Then find the inverse, identify its domain, range, and any asymptotes. So the parent function is y equals the natural log of x. The base is base e, so it's the increasing log function, and it looks like this. And it goes through the point 1, 0, e, comma 1, and 1 over e, comma, negative 1. We have a transformation. This transformation is 2 to the left. All right, let's go ahead and graph it with the transformation, 2 to the left. So let's have the vertical asymptote here at negative 2. And so then we have this point, which is negative 1, comma 0. And we're going to have another point right about here. The x-coordinate of this point here was e, so if we're going to move that over 2, it's going to be e minus 2. There's no real way to simplify that unless you're going to use decimals, and we want to be exact on this one, so we'll just say e minus 2. Same thing for this point here. The x-coordinate was 1 over e, so this point is going to be 1 over e minus 2, comma negative 1. And there we go. So the domain of this function was negative 2 to infinity, open at 2. The range is negative infinity to infinity. And the vertical asymptote is x equals negative 2. Now the second part of the problem is to find the inverse. So let's go ahead and do that. So find f inverse. And we know how to do this from some previous sections. So we start with y equals ln of x plus 2. Switch out the x and the y. And we get x equals natural log of y plus 2. And now we need to try to solve for y. So the first thing I'm going to do is I'm going to take this log form and I'm going to switch it into its exponential form. The base of the natural log is e, so we're going to get e raised to the x power is equal to what we're taking the log of, y plus 2. So take a second, think about how that came about. The base is e. The exponent on the e should be what the natural log is equal to, which is the x. And then e to the x is equal to the argument of the log, which is y plus 2. All right, and now solve for y. So we get y is equal to e to the x minus 2. So that's the inverse function, e to the x minus 2. Then we want to graph it. We'll just do a little graph here. E to the x is the increasing exponential. It's been shifted down 2 units. So here's the horizontal asymptote. It's going to go through -1, 0 and go up like that. And then the domain is -infinity to infinity. The range is -2 to infinity. And the horizontal asymptote is y equals -2. If you were to have graphed the inverse function here and the log function there on the same graph, then they would be symmetric over the line y equals x because they're inverses. Example 8, solving equations using logs. Solve log base 4 of 5x plus 1 equals 2. The easiest way to do this one is to convert this back into exponential form. So 4 to the 2 power is equal to 5x plus 1. 4 squared is 16, equals 5x plus 1. So we get 5x is equal to 15, and x is equal to 3. Next, we have one of our connections. We want to connect with medicine. The number of milligrams of a drug found in the bloodstream of a patient t hours after it was administered is given by m of t is equal to 6 times e to the negative 0.2 times t power. How much of the drug is in the bloodstream after an hour? So we want to find m of 1. Be sure and use the correct notation here, m of 1. And that would be 6e to the negative 0.2 times 1, which is 4.91 milligrams. Question B. The patient should receive a second dose after the amount of the drug remaining in the bloodstream reaches 0.5 milligrams. How long after the first administration should the patient receive the second dose? So the question is asking, after how much time will the concentration reach 0.5 milligrams? So we want to solve m of t is equal to 0.5. Well, m of t was 6e to the negative 0.2 t. That's equal to 0.5. First, I want to divide by 6. And I'm not going to work anything out yet. I'm going to wait till the end with the calculator to work everything out. And there are many ways of doing this. If you're new to logarithms, this is the only way that we have so far, and that is to convert to log form. So I'm going to go ahead and convert this to log form. And when we do that, we end up with the natural log of what the exponential is equal to, the argument, 0.5 over 6, is equal to the exponent, negative 0.2 times t. Then to solve for t, we take this entire side here, natural log of 0.5 over 6, and we divide it by negative 0.2. When you work that out on a calculator, you get 12.42 hours. Question C says, sketch the graph of y equals m of t and on this window and mark the point where the second dose is administered. So these are window coordinates here. They are in the form of the x-min, the x-max, and the y-min, and the y-max. So you can go ahead and enter this on your calculator and draw a little sketch. You'll create a little box here. And when we do the axes, we can do it like this. Be something like this. This will be the t-axis. This will be the m of t-axis. And you should notice that the x-intercept is at 6, and that it's the decreasing exponential. So it should look something like that, maybe, probably a little steeper even. And then somewhere around here is the point where the second dosage should be given. So be sure and do that on your calculator and make sure you can see these results.